Hey, what's up everyone? Sam here from This Week in Machine Learning and AI. The video you're about to see is our final TWiML online meetup of 2017. In this meetup, we recap some of the major ML and AI advancements of the year and take a look at some of the key trends we'll be tracking for 2018, including deep reinforcement learning, capsule and schema networks, and more. For our main presentation, Bruno Gonçalves joins us to discuss the paper Understanding Deep Learning Requires Rethinking Generalization by Google Brain researchers Shiyuan Zhang, Sami Bengio, and others. As a reminder, we hold meetups monthly where we discuss classic and hot papers in machine learning and AI, and we would love for you to join us. If you haven't registered yet, head on over to twimlai.com/meetup to sign up. Enjoy the meetup, and of course, if you like what you see, please, please, please hit that subscribe button. Enjoy.
Hmm. Hmm. LOL. LOL. Hmm.
All right. So how's everybody doing?
Hmm.
Good, Sam. How you doing?
Doing great, doing great. So I am looking forward to Bruno's presentation today. I powered through that paper earlier today, so I have a bunch of questions. Looking forward to grilling you on them, Bruno. Um, so here is our agenda for the hour that we've got lined up. So we'll start with actually this intro, and kind of that will flow into a kind of open mic, if you will, community discussion. When we publicize the meetup, we encourage folks to come with their thoughts on interesting stories and developments in the world of ML and AI from over the course of the past year. I'll encourage anyone who isn't speaking and might have some background noise to mute out. There are some noises coming through. I think I got one of them.
I'll mute out here, Sam. Just wanted to say congrats on the million
Nice.
followers.
Thank you, thank you. So I think I got the noisy one. So we'll jump into that community discussion, and then this is a holdover from our presentation will of course be delivered by Bruno today, and he's got about 45 minutes for the presentation, including Q&A discussion, whether that is questions that come up during the presentation or afterwards. And then we'll briefly wrap up. So we've tried a bunch of different ways to kind of manage the Q&A. We've got a pretty big group today, so we'll continue to play it by ear in terms of whether we use the Slack channel, the Meetup channel on Slack, or whether we use the Q&A on Zoom. Keep in mind that it's difficult for the speaker to both speak and pay attention to the Zoom channel. So Bruno, I'll pay attention to the questions as they come in and kind of funnel them to you. You don't have to worry about that so much.
Excellent, thank you.
And so hopefully I didn't just mute myself. I muted the other lines. And then in terms of the meetup for 2018, we are still solidifying our lineup for 2018. A number of you have indicated interest in presenting as you signed up for the meetup. So by all means, if you're interested in speaking in one of the slots next year, please shoot me a note or send me a DM or however works best for you. So in terms of discussion, this is our open discussion time. So I don't really have a lot of prepared, commentary or remarks here. So I'm looking for folks to kind of unmute and chime in terms of, things that they'd like to spend a few minutes chatting about. And I've got some kind of prompt questions here. The first one is the one that I mentioned earlier. So, what do you think are the most interesting and important developments in ML and AI in 2017? But I've got some others as well. What, trends are you looking at going into 2018? What do you think is the most interesting, the most important? If all else fails, I hope everyone has a favorite TWiML podcast from the past year. So let me know which of those is your favorite. And you don't have to say Bruno just because he's on the line. And if there are specific topics or guests that you'd like to hear more about in 2018, let us know that as well. And of course, our standing questions: what are you working on? What did you see in the past, few weeks? Any interesting papers or projects? So now I will just open it up. If you've got something to say, just unmute and chime in. And don't let it be silent for too long because it makes me nervous.
So I think, hey, this is my name is Brad. I'll start off the conversation, I guess. I think one of the important trends in ML AI going into 2018 is reinforcement learning. And I feel like there have been a lot of developments in it in 2017, but also there's been a lot of emphasis, especially in people jumping on the deep learning train, myself included, on things such as really supervised learning methods like RNNs and CNNs. And I feel like reinforcement learning is not as prominent as it perhaps should be. And I think in 2018, at least I hope that there's a lot more in that realm, I suppose.
Yeah, I think you are right on target, and that is an area that I am really looking forward to digging into in 2018 as well. I'm curious what what if anything you've got planned to kind of further dig into it. I know for myself, I want to take a look at. There are a couple of open source environments out there. OpenAI Universe is one, and this year Unity Technologies released Unity machine learning agents. I think is like a environment for training reinforcement learning agents. Both of those look really interesting and are things that I want to dig into over the coming year. Are you planning anything, Brad?
Yeah, I mean, OpenAI is definitely, especially after I listened to your podcast the other day with Greg Brockman, I believe his name was, and
yeah.
I definitely got me more interested in dabbling with OpenAI, and I think just the whole concept of artificial general intelligence and what it'll take to get there. I guess like my view on this is that something like these RNNs and these CNNs are like really great and like computer vision's awesome, but they're just very limited in what they can do like on their own. And so I really like the idea of, I guess, reinforcement learning almost building a virtual world, I suppose, like, if you will. And I think that a lot of what OpenAI is doing, and they're the fact that they have these scaled down worlds, if you will, and even something as simple as like Super Mario Brothers, and I'm hesitant to even use the word simple, but there's only 6 things you can possibly do in that world, but still, like, even just having something understand what's going on in a world such as that, you can only go up from there, and you can keep growing. So definitely, yeah, I mean, just to answer your question flat out, I think OpenAI is definitely where I want to look into, and I think they're definitely onto a lot of really cool and interesting things in this space.
Yeah, I think the idea that reinforcement learning in some ways represents kind of the way people learn or the way babies learn, like just by being in an environment and trying things as opposed to being given a bunch of questions and answers. That's really kind of an interesting and compelling proposition. And I think there's a ton of potential there.
Yeah, absolutely.
Anyone else want to chime in?
Add on. Yeah, this is Michael. Can you hear me?
Hey, Michael, how you doing?
Good. How are you?
Good.
I'll add on that I think what is really exciting to me about the reinforcement learning stuff is the notion of pairing it with robotics, particularly at manufacturing plants, right? So the idea that they can train out an AI, and then sort of wire it into a physical presence, a robot in your manufacturing plant for assembly or whatever. I think is actually really powerful, and I'm waiting to see that play out in the next year or two. But I think that's where, in my mind, a lot of the algorithms that are not begin to have real value.
Yeah, if folks are interested in that particular topic, I would encourage them to take a listen to the podcast I did as part of the Industrial AI series, in particular the one with Peter Abil, who I incidentally met for the first time in person just last week at NIPS. And in fact, at the time of the recording of that podcast, he was at OpenAI. He recently left OpenAI to start his own startup to kind of go after this space in a more, focused, or shall we say, or commercial way. And so, he also thinks that it's an interesting space and one that's going to see, a lot of commercial traction over the next few years. There was also one with Chelsea Finn, who I also caught up with at NIPS, and we also talked about kind of this robotic learning space. And in fact, an interesting counterpoint to the interview with Peter, who kind of takes the perspective that, hey, we should throw everything into deep learning and let deep learning figure everything out, is a conversation that I did that will be coming out this week with, the name is escaping me right now, but I will share it. Momentarily. Actually, let me look it up. Anyone else want to chime in while I'm looking this up?
Yeah, hi, I'm Dan. I wanted to add that I just saw a great talk by the CEO of Vicarious at the something hosted by the Creative Destruction Lab at UT. Okay. It's on YouTube, and it was reinforcement learning, but instead of having like a standard deep learning system involved, it had something called schema networks, and that was a very interesting paper. But kind of arguing that it was like a probabilistic graphical model for like building a world model while doing reinforcement learning for, and it was Atari games, but I'll post a link to it, but it was very cool. And I don't know if you're familiar with Vicarious, but they've kind of got this idea that deep learning is only going to get you so far, and you have to get down into like more causal world models and stuff like that to make it all work out in the end for AGI.
Interesting. So I will come back to that in a second. Just for folks who are waiting for the answer to the previous question, it's Aaron Ames, and it's a show called Integrative Learning for Robotic Systems. He's a prof at Georgia Tech and has a robotics lab there, and I did an interview with him the week before last at reInvent, which was a really, really, really good one. So I've come across the name Vicarious, but I don't think I've spoken with anyone there. I don't know, I haven't looked into the schema networks thing at all. But there's this other, I don't know if folks have heard of Capsule Networks, but that's Jeff Hinton's a new approach that he's been promoting recently that also claims to kind of go beyond what deep learning is able to enable. Has anyone dug into Capsule Networks at all?
Yeah, I was just reading that one today. That's tough to get your head around.
Were you reading the Medium post? There was someone did a Medium post, kind of like a two.
I saw that. I was actually just reading the archive paper, the dynamic routing one.
Okay. Yeah, I didn't even get to the paper. I started reading the Medium posts, and I think it simplifies it, but I think it still is kind of a shift in the way we think about things that takes a little while to get used to.
I think the gist of it, though, was that convolutional neural networks work better than they should, and that and that capstone networks deal with kind of rotations and skews in different dimensions. So it kind of is able to track forms of visual objects that may be partially obscured. So in theory, they should be more efficient than a CNN.
One of the interesting topics that came up at NIPS, actually, it came out of a talk or a keynote given by one of the winners of the, I forget the specific name, it was like the Test of Time Award paper. So the recipient of that award came up and gave a talk, and basically, you may have seen this on Twitter or wherever you hang out, basically said that deep learning is like alchemy, and kind of issued a call to arms for more rigor in the field, which, speaks to this whole kind of the unreasonable effectiveness of gradient descent and like how this stuff works really well, but we don't really understand how it works, which is actually kind of a great segue into the paper that Bruno's going to present, because this is an attempt to by researchers at Google to understand and put some theoretical bounds and constraints around the performance of deep neural networks. And so with that segue, I think it is time to hand the baton over to Bruno.
Hi, Sam. Thanks again for inviting me and letting me do this again.
Absolutely.
So
I think you can just kind of share your screen.
I'm trying to share screen. Yeah, I can do this and share screen.
While you're doing that, I noticed that some folks dropped some links in the group chat about the things that we were talking about. Thank you for everyone who did that, and I'll take a look at those and share them around.
Okay, so can you see my screen now? You should see it.
I cannot, but
it's.
I'm still sharing, so let me stop my share. Okay, there we go. I'm seeing your screen.
Okay, so you see a guy swimming. That's good.
Unlike any swimming I've ever seen before, but yes.
He's got his laptop. He's deep learning. So.
Yeah. Nice.
So and it's water cooled too, so it's more efficient.
Awesome.
So like Sam was saying, I think, and me personally, I think that in the future, and probably next year, one of the big problems that people are going to have to face is actually understanding what these methods are doing and how they are working. Right? You can't just keep trusting them as if we were alchemists, but you need to actually understand the magic and what's behind the magic and turn the magic into science. Right? And right now, everybody's eager, and I'm very happy that they're doing this, of throwing neural networks and deep learning to every problem you can think of. But you also need to, at some point, to stop and think and try to analyze what the problem is, why it works, why it doesn't work. And I like this paper in particular because it made me think a lot about this, but also because they don't try to make too many claims. They don't try to say, okay, we solved it, we understand why it works. They basically say, we tried all of these things, we still don't know why it works, but here are some clues. Right? So I think it's more of a way of starting the discussion than actually a way of finishing it somehow. And there are actually several papers I already am reading that are follow-ups to this to try and understand better what other people have been doing and even try to understand this paper better. So, so moving on. So everybody's familiar with neural networks. There are different types of architectures. There are, of course, there is of course a large interest in these deep convolutional networks, these deep feed-forward networks that somehow bypass the obligation of having to define the features by hand, of having to perform some type of feature engineering to begin with, but somehow, and this is the part that's not really well understood, they are learning these features themselves automatically, just through the training process, through using stochastic gradient descent type methods. And so the idea is, how are these things actually working? Why do they work? And why do they work so as well as they do? Right? Could it be that they're just memorizing everything, right? Maybe, maybe not. So, but this is what this paper tries to tackle somehow. So ideally, you're all familiar with supervised learning. You've been to school, so you've seen something like this before. And the way it works is, the teacher will explain something to you. They'll give you a bunch of examples in class, and then you're expected to generalize from these examples and apply this knowledge to new examples that you haven't seen in the exam in a new situation. Right? So supervised learning in the same way works in a similar way. Right? It's given a bunch of examples with labels, and it has to learn how to predict the labels given the examples for examples that it never saw before. Right? But the question is, how is this actually happening? So even if you have a simple network, 2 layers, 3 layers, 4 layers, how are all these weights cooperating in a sense to learn and to be able to generalize and to apply to new cases? And is it possible that they're just memorizing everything? So we don't know. Of course, memorization is not necessarily a bad thing. I mean, there are machine learning algorithms that rely exclusively on memorization, like the case of k-nearest neighbors, where you just keep track of every example you've seen. And then for every new case you look at it, you compare it with the examples you've seen before, and you choose the one that looks more similar, and you say, okay, this is the correct class. Of course, there are other complications. You can adjust the weights on how, if you think that some examples are more important than others, or based on the distance between them, etc. But this is the idea. You memorize everything, and then you look at the new example you have, and you compare with your memory, and then you try to guess from there. Right? So this can be very effective, and it's actually very useful in many situations. And it's one of my favorite algorithms because it actually works pretty well, and you understand exactly how it works. And the results are actually pretty reasonable in many cases, many situations. Now, but this brings us to this idea of how do you actually evaluate these models, right? So how do you have this trade-off between how much you memorize and how much you're learning, how much you're generalizing, right? So just to define a little bit the terms here. So when you're doing the training, so when you're in class, if you're a student, with more examples that you see, with more classes, more class time, somehow you're learning more. So you're reducing the number of errors you're making in class. Right? Of course, every time you take a test or you take an exam, you know that the error will be higher because you're trying to generalize from the problems that you've seen before to new problems, to new cases. And ideally, what would happen is you would find the exact point where these two curves start diverging. Just to clarify, we call the error bias in the training bias. So this is the errors you make during class. The difference between the class and the exam is called the variance. And of course, there is this trade-off between a high bias, so high error, and low variance, where you do the same thing in class as well in class as is in the exam, or in the opposite case, where you do very well in class because you memorized everything, and you do very poorly in the exam because you're not able to generalize. Right? So what you want is to find this nice medium. So the question is, can we understand this, and can we understand how this actually relates to deep learning and to these deep networks? And of course, because we know overfitting is bad, right? You want to minimize the variance that you get between the training and the testing. Okay. Now, and to do this, what the authors did is they came up with this experimental setup. And this is a really cool thing, I think. So they have basically this generic machine learning machinery where you have inputs, you have some algorithm in the middle, you have outputs, and this is what you're using to training. So this is a normal thing. In your input, you have images. In the center, you have some type of algorithm, some type of implementation, inception, etc. And then you're trying to predict the labels. Right? And if you're trying to understand how well this type of machinery can generalize to things it hasn't seen before, one of the possibilities, one of the way of doing it is basically introducing noise and errors at different parts of the process, right? Different stages of this process in each of these 3 blobs, let's say. And they do this in multiple ways, right? So they starting with the input, they shuffle some pixels. So they kind of blur the image. They replace it completely with random pixels. they generate pixels completely at random using a Gaussian distribution. So this is one way of affecting the input. In the middle, they test different algorithms. They have the inception network, they have AlexNet, and they have MLP, if I'm not mistaken, yes. And then in the output, they also perturb it in different ways, but either by looking at the true labels, trying to predict what is the actual result, what is the ground truth, to partially corrupt the labels. So for some fraction of the cases, you just replace the correct answer with the random answer, and just completely random labels, so completely random answers. And by playing with these three ingredients, they're trying to explore basically what happens and how well do these procedures still work or not. So that's the general idea. The data sets, of course, are standard data sets. You have CIFAR and you have ImageNet. They have very different sizes, which is actually interesting. In the case of CIFAR 10, you have 50,000 training examples, 10,000 validation examples that you're supposed to classify into 10 classes. Each image is 32 pixels by 32 pixels and has 3 channels of color, so red, green, and blue, the usual. On the other hand, ImageNet is much larger. You have 1.2 million training examples, 50,000 validation examples, and you have 1,000 classes. So it's much more fine-grained in a sense. And the images are also higher resolution, so you can actually contain more information and be more detailed. Now, so to answer the first question is, are we actually memorizing everything? Are we learning the noise? To some degree, they do a few examples. So what we're plotting here in the first figure, in figure A, are the learning curves. So this is basically how much is the error, the average loss of the process changing as you increase the number of steps of training, right? So in an intuitive way, the more, based on how long you spent actually in class, how good are your answers to the teacher. And here you see something very interesting. So for the true labels, that's the blue curve. You have the usual behavior that the error decreases, eventually goes to 0. So here they're actually forcing it, and this is by design, to have the error always go to 0. So they're waiting until the network answers correctly to every case in the training examples. Mm-hmm. And then they try shuffling the pixels, and that increases the error, of course, because especially in the beginning, you're just doing random guesses almost. And then gradually it goes to 0, and eventually with completely random labels. So there is no correlation, there is no structure in the data, there is nothing connecting the output with input. You're still able to get the error to 0, and you're still able to learn and get the correct answers. So if you think about this, this is really amazing. So what it shows is that when you're introducing noise, even when you're introducing noise in the labels, you're still able to train it. It will take longer, but you're still able to get there. The reason I suspect, based on this paper and other papers, why it's taking longer when it's completely random and just, in a sense, forcing it to memorize noise, is that especially in the beginning, what the network is actually able to pick up on the structure of the data, like on actual correlations in the data, and use that as a foothold to learn more complex patterns, right? When there are no patterns in the data, then you can see in the beginning, the training and the improvement is very slow, right? But when you actually have structure in the data and it's real data with real labels, you can see how the error goes back very quickly, because it's very easy. You can think of it as a way that it's very easy to somehow summarize the data, to summarize the pictures and say, okay, this picture looks a lot like that picture. While here, all the pictures, because they're completely random and have no association with the label, have no structure. So you can't really try and find common points, and you actually have to, in a sense, memorize everything.
One of the interesting nuances here that they called out in the paper is that while clearly it takes longer in terms of the number of steps, and it takes longer, as you mentioned, for it to it's like it takes the network a while to figure out that you're just messing with it, but then once it does, it converges pretty quickly.
Exactly. So it's actually and I say, and it's something it's easy to, in a sense, anthropomorphize, but they don't really understand. And we always get the perfect overfit where you get exactly the correct answers.
Right.
And here on the second plot, what it's showing is basically how long it's taking to overfit to reach these 0 errors based on how much you mess with the labels. And so here you're replacing a given fraction of labels with random labels and seeing how much longer how much harder that's making it to the problem to work out and for the network to learn. And of course, the more you corrupt the data, the harder it is. Different algorithms behave differently. So inception takes the longest to converge. It's also the most complex structure. AlexNet is the best. MLP is actually in the middle, more or less. And you see here also the test error, of course, that as much as you keep increasing the number of corrupt labels, what you're doing is essentially giving it random noise, and at the end it's just randomly guessing in the testing examples. So since you have 10 classes, you're randomly guessing. You have one shot in 10 of guessing correctly. So 90% of the time, 9 times out of 10, you'll be wrong, right? And that's why it's converging to 0.9 over there. So moving on, yes.
Now, before you move on, this is one of the first key results in the paper. Does anyone have questions?
Yes, please feel free to interrupt me at any time. Don't be shy.
Or comments?
Insults?
Observations?
Is anybody out there?
Hey Bruno, this is Sharat. Hi Sam. So, so it's, in a sense, it seems like there's something about the network. Overall, I felt like when I was reading the paper, like every sentence I read, I had to stop and think about for a while. And I feel like I follow it. But then when I get through like 2 or 3 pages of it, and I'm trying to distill the essence, I feel like, oh, I need to go back and fit these pieces together.
Yes.
So in this case, it seems like, so there's something about the network intrinsically that that makes it good or bad in terms of likelihood to overfit, right?
Yes, so this is related to the structure of the network, right? What layers it has, how the layers are connected, how many parameters there are, and this they kind of show very quickly at the end, and it's in a kind of way, with their theorem that you need to have a certain size of the network to be able to do these things, right? Otherwise you're not able to memorize everything. So it's showing that there is some type of memorization going on, but there is probably something else as well.
Right, and the thing is, that's not surprising when the labels are correct. But then even in like a random label scenario, there's still something about a network structure itself that makes it hard to overfit, or like, time to overfit be much higher for a quote unquote good network.
Yes. So this, I said,
maybe are we specifically focused on the observation and that's in B in this picture, like comparing the networks?
Yeah, the B convergence slowdown, yeah.
Yeah, I mean, also it should be kept in mind that these networks have very different structures and very different sizes. So it's not, and inception is by far the most complex of them, that has the most layers and most parameters. So it's not too surprising that it's the worst of the 3. But the important thing to notice here, I think, is that the behavior is always more or less linear, right? You're increasing the number of errors, and the time it takes to overfit, it's increasing smoothly. So it's not exploding exponentially. It's not a power law. It seems to be more or less linear-ish, let's say.
So the slopes here, or the magnitude of the slopes here, are correlated with the number of parameters of each of these models.
I would suspect so, yes.
So I took the takeaway for me in this was, like, to make it really simple, that these networks are capable of remembering all of the inputs if you train them enough, and that's like I think that's like the kind of the opening act of this paper, and then they go into some other. Then they kind of extend from there to talk about how we don't really know how generalization works. Is that oversimplifying it too much?
No, I mean, it captures the right idea, I think. And they even say that maybe we can't even talk properly about generalization because we don't even understand how it's working in this case. Right? We just know that it's capturing something. It's able to apply it to other examples, but it's not clear why, right, or how it works. That's why I started with the example of the k nearest neighbors, because to me, at least intuitively, that seems to be like the closest example, right? It's something that you can understand, and it seems to be doing more or less the same thing, right? It's memorizing all the examples, and then from that, it's generalizing in this simple way. Here, of course, it's generalizing in some more complex way, but it's still the same fundamental idea, I think. So.
One other thing I'd like to say is that in B, it's really surprising that the MLP like splits the difference, because I mean, C makes sense that it's kind of like ordered in terms of complexity, but have the MLP split between AlexNet and Inception is really kind of strange to me.
No, I mean, it's the one with the size in the middle, in a sense. So
it's actually, that's what I thought, but I think what Dan is calling out is that it's actually, in terms of the number of parameters, it's the one with the least parameters.
Yeah, but it's also the one with the highest levels of error, right? So it's the least efficient in learning. If you look at C, right? It's the one that always has the highest errors. So it's the one that's learning the least.
Okay.
So it's kind of maybe something like the bias variance trade-off. So here it's the complexity error trade-off, right? You can make the network more complex, so it will be better at learning, but it will take longer to learn. Or you can make it simpler, and you're able to train it faster, but you get many more errors, right? Does that make sense?
Yes, and just to expand on that, without kind of seeing these networks, looking at these networks in front of me, the number of parameters does not fully capture the complexity of the network. There are other factors like the layers and the width of the layers and all that.
And the way the layers are connected. And,
right.
And there's all sorts of things. But I was reading some paper, some other paper recently, also in preparing for this, and they were saying that you can almost think of the structure, so the architecture of the network, almost like the prior, right? Like in Bayesian analysis. So in Bayesian, you know that if you have the right prior, things you converge much quicker to the correct value. While if you have the wrong prior or an uninformative prior, it will take you much longer to get to the right answer. And they were saying that somehow the structure of the network is acting as a prior, right? So it's conditioning how fast you can go and how long it will take you to get there.
Yeah, but I mean, in this case, AlexNet and Inception are CNNs, and MLP, I assume, I actually didn't read it, but it's just densely connected or something?
Yes.
So it's strange that it like splits the two CNNs, you know?
Yeah, I mean, but I don't think there's any like deep meaning to that. I mean, I think it's a combination of the complexity of the different networks and how long they're taking to train. I think here the important message is that even when you increase the level of errors, you're still able to get to the perfect overfit. It will take you longer in some cases than others, but the increase is still relatively predictable and linear. And so the slope of these curves is still more or less well behaved.
Okay.
More questions for this slide?
Not for this slide, no.
Okay. So then let's move on then. So, and like I mentioned, of course, the correlations in the data, so structure of the data improves the learning. So the more structure you have in the data, the easier it is to learn. And like Sam was saying, if you confuse the network in the beginning, it will take a while, but then you would eventually figure it out. And so here we're looking, actually here we have the number of parameters in the network. And yeah, so you can see that the 512 is actually 1.2 million parameters, while AlexNet has just a few more, and Inception has a lot more, 1.6 million. So in terms of parameters, it's actually the smallest one, but the structure is also very different, and it's a lot less structured. Right? So one of the things that's also important in the architecture of the network is how many layers you have. Right? So how deep the network is, because that means that somehow defines how complex the features it can learn from, right? If you only have one layer or two layers, the features it's able to learn will be relatively simple. But the more layer, but each layer you add is somehow combining the features from the previous layer into new features, right? So they can be more complex features and capture more structure in the data, right? This is why you get in these convolutional networks, you get these beautiful pictures of first edges and then circles and then eyes and then faces, because the network itself is figuring out these different features at each level, and at each level, the features of that level are combinations of the features from the previous level.
Mm-hmm.
Right? And here what they're seeing is basically how good the answer is when you move so what is the training and testing accuracy when you start messing with the inputs again, right? So here what they're doing is they're adding data augmentation and different variabilities, random cropping. So this is what this means is they'll grab the original image and they'll crop it in different ways, right, in random ways. And the weight decay is basically, in a sense, a normalization term, right? And even with all of these changes, you can still train it until you get perfect answers, either 100% or 99.9%. So so you can overfit it perfectly. And then of course you have to compare what is the accuracy in the test, what is the end result. And this, one thing it's important to mention, is in most cases, except in the grayed out ones, they're training with they're testing it with the actual results, with the actual labels, and not with random labels. So only the gray ones are random labels, and that's why you have high levels of accuracy even in the test data sets.
Mm-hmm.
Right? But one thing that's important to mention here, so you have random cropping, so this level of data augmentation actually provides the best results. So the fact that you're adding these variations on the input images is actually improving the answers you're getting. So you can get 89%, even in the test case, 81, 79. But when you remove this, you get the biggest jumps, like to 86, 85% in inception, 77, 76. So you get the biggest gap if you don't do the random cropping and you just do the weight decay. So if you just try to normalize and regularize what are the weights that you're training.
One thing that I don't recall them mentioning was whether the random cropping was adding training samples, or was it just a transformation that they were applying to a certain number of samples?
So basically what they're doing is they're generating new input images
mm-hmm.
by modifying the original ones.
Right? And replacing them, or
adding them.
Okay.
Right. So you get you're giving it more data. So you're giving it more data, right?
Right.
And that's why it's called data augmentation. You're augmenting your data set by doing these tweaks.
Right. And so you could, I don't know, maybe this is, I don't know how meaningful this point is, but you could argue that the test accuracy could come just from having more data, as opposed to the fact that it was specifically this random crop or some particular information.
Yes, I think that's actually one of the points that's interesting from this, is that you do that. Actually adding more data is what's making the difference here, I think.
Mm-hmm.
Because you can see that if you just put the weight decay, whether you have it or not, will make a small difference. But the biggest jump is between having this extra data or not having this extra data. Right?
Mm-hmm.
Right. It doesn't look like the test accuracy difference for the random crop yes or no is particularly significant, right? But so I wouldn't. It doesn't seem to me like you should put much weight in that as a positive factor. On the other hand, it's interesting that it doesn't degrade it, right? You would actually expect a degradation of result, not a small improvement in the result.
What do you mean by adding more data? You would expect?
No. By adding the random crop, you would expect a degradation in the test accuracy.
No, actually, because what you're doing is you're giving it, instead of giving it exactly the same picture, you're modifying it a little bit. So you're making it more robust to variations in the data, right? So
Okay.
You're letting it explore a little bit more all the possibilities. Right?
Yeah, augmenting vision data with like brightness variations or rotations or even just like jitter, like or just a little Gaussian noise.
Yeah, I mean, this is a standard computer vision technique. So it's expected that it should do better. I believe, like Sam was saying, that this is doing better because it's seeing more data and it's seeing more variations of the data.
Yeah. Okay. Thanks.
And this 3% difference, 3.3%, it's actually significant. I mean, there's been papers written that were improving on previous results by 3%, 2 or 3%. So it's not a trivial variation necessarily. So, and here the conclusion, at least for me, is that this data augmentation helps reduce the variance. So, and variance, if you remember the original definition, is the difference between the test accuracy and the train accuracy. It's the gap between the two results.
Going back to like people's interest in RL, I think it was TWiML AI I was listening to the other day. I love that podcast. Talking about how adding a bunch of like random noise and crap to the back of the RL environment made a big difference, right? Like crazy color patterns and everything.
Yeah, I mean, I think that's the same idea, right? You're adding more data, so you're able to train the network a little bit better. You're giving it more variations.
Yeah, and you're saying these variations are not what matters. Focus on the stuff that's not varying. Right?
Yes. Because it's saying, okay, you can ignore all of these parts because the answer is the same as long as you have as long as the car is there. It doesn't matter if the car is a little bit more to the left or more to the right. It's still a car, right? So that's what you're saying, that the position. So this is one way of adding basically translational invariance, that the position is not important. And this is also and this translational invariance and rotational invariance is actually one of the reasons people do these convolutional networks, right? They add these convolutional layers to try and add basically to add this invariance to the data, right? Sorry, somebody was saying something? Yeah.
Yeah, hi Bruno, thanks. This is a great discussion going on. I just wanted to understand if you have the figure in terms of percentage of new data which is being added because of this random crop.
I don't have it here now. I mean, it's probably in the paper somewhere. I don't have it off the top of my head.
Okay, no problem. Thanks.
Yeah, I don't recall seeing that, and I agree. I think it's a significant detail, or at least an interesting one. Maybe it's in that table that's in the back of the paper.
Yes, I don't. Yeah, I don't remember, to be honest.
Yeah, I think it's in Appendix A. If it's anywhere, it's in Appendix A of the paper where they talk about the methodology.
I have the paper right here.
I think it's just every time the input example is presented, it's just randomly cropped.
Yeah, so that's a very different thing from what that was my question. Like, I think when I read random crop, that's kind of what I think of. But when I read data augmentation, I think of randomly cropping a priori and then throwing some of those random crops, maybe scaling them back up and then throwing those into the data set. And I'm not real clear on which one they're doing here.
I mean, it's equivalent, I think, right? What they're explaining, they're saying this in footnote 1 in the last page. In random cropping and augmentation, a new randomly modified image is used in each epoch, but the randomly assigned labels are kept consistent for all epochs. So what this means is that basically every time that they go through the data set, they modify it a little bit. But this is the same thing as having a larger data set with all the modifications kept constant. You're just doing it in memory instead of doing it in keeping them in the hard drive.
Right. It would be like looking at all possible crops and duplicating your data set to that and then using that.
Right. But each training epoch has the same number of examples. We're not adding the number of examples in training epochs that include random crop.
Yes. But in total, you're giving it more examples. Right?
Yeah.
You're modifying them every time.
Right.
So in a sense, even how much?
Hello?
Say that again, Sharth.
I think it's too much augmentation, at which point you're training.
You're breaking up.
You're dropping in and out. You can try typing it into the Zoom chat.
Oh, sorry.
There you go.
No, I was just a thought that I was wondering, like, certainly augmentation helps because it reduces, like, it lets the model see, like, more variation in the training data.
Yeah.
But it's almost like it's possible to see too much variation to the point where, like, there is a mismatch between train and test distribution. And so even how to augment and how much to augment itself is like some kind of a, hyperparameter.
Yeah, although this paper kind of argues that, at least from the perspective of the network learning, you can throw whatever you want at it, and given enough examples, it'll figure it out.
Yeah.
But I certainly agree from like a practical perspective.
Yeah, I mean, if you crop it too much or do too many crazy things, you're basically adding noise to the input, right?
Right.
Which we already saw in the beginning. What we would do is would slow down the training process, but you would still be able to learn everything.
Okay.
Okay, can we move on then?
Yes.
Okay, so continuing this idea of the data augmentation. So here now they're looking at data augmentation, but also now with dropout. Right? So what dropout means is that for each training step, you are basically ignoring some of the weights, a fraction of the weights that are randomly chosen. And this has been shown in many different papers that this actually improves the results significantly, because in effect what it's doing is, instead of having the original network and that you're training one original network, what you're doing is almost as if you were training an average, so an ensemble of smaller networks, right? So if you have a 10% dropout, that means at each step you're ignoring 10% of the weights randomly chosen. So it's like you are training an average network that is 10% smaller, right? But since you're doing the average over different realizations of this network, you're able to get better results, right? So it's kind of, in my head at least, it's the same intuition as doing a random forest instead of doing a random tree. And you're taking the average and the combination of different results, but you're putting them together in the same way. And here again, we show that you can still memorize everything. So you can still get pretty much 99%, 100% results, even with random labels. The results are slightly worse in some cases, but not too much. But then when you, without the dropout, you can see that the results are significantly lower, right? So in the right-hand side, in the top 1 test and the top 5 test, you drop from 73% almost to 60%, and on the top 1, and from 90.5 to 80.3. So it's a huge drop. So this is making actually an important contribution, because again, it's adding somehow variability to how the network is looking at the data, right? So here, in a sense, if you think in the case of without augmentation, so just the original images, by adding dropout, it's like if you have instead of adding noise to the input, you're adding noise to the network and making the network less reliable on specific neurons. So it's kind of, it has to learn to take a pull over all the different weights and all the different neuron structures, if that makes sense. Okay, so no questions. And so finally, moving on. So the final thing that they're looking on in terms of these different experimental setups, different experiments that they're running, is to look at these implicit regularizers, right? And so data augmentation is one implicit regularizer. The weight decay is this basically this regularizing on the weights. Batch normalization means you're normalizing for over each batch instead of the whole epoch and instead of the whole data set. And you can see again first that there are cases, at least in the case of ImageNet, that it would be better for you to stop training at a certain point, and after that you're actually losing accuracy in the testing cases. Right? Of course, for the training cases, you always go to 1. If you wait long enough, you always memorize everything. In this specific case, it's actually shown, and that's highlighted by the shaded red area that you see next to my big arrow, is that you're actually getting more confused as you're adding more data. Right? You're making your life worse, which is interesting. And this seems to depend also on the structure of the network. So you see that in ImageNet, but you don't see it in the CIFAR 10, in the inception case. So it depends on the data set that you're using. And I imagine on the structure of the data set and on the structure of the classes, right? With ImageNet, you have a lot more classes. You have almost 1,000 classes. With CIFAR, you only have 10. So somehow CIFAR is a bit simpler. So maybe it's not as likely to get this confused. Although you still see that a little bit in the inception without batch normalization. So the thick red curve over there. And as usual, there is a big gap between what you can get in the training, which you can go all the way to 100%, and in the testing, that of course you're making mistakes. And again, just to emphasize, you have these high accuracy results for the testing cases because you are keeping the original labels and not shuffling them in any way. Does that make sense? And here you can even see how the removing the batch normalization is actually reducing the accuracy a little bit in the test, although not by much, by maybe at 1 or 2% over there. So the data set itself also affects the generalization. So somehow this is also taking into account how complex the data set is. And I suspect that's why you see that in the ImageNet, which has many more classes, so it's more complex. And you see that here early stopping might be useful, while in the case of CIFAR, which is a simpler data set, it might not be as useful.
Mm-hmm.
Right? Because maybe it doesn't get, since it has fewer classes, maybe it doesn't get quote unquote confused as much. So there's no benefit necessarily to stopping early. So, and just to finalize, the final point, which is not exactly the final in the structure of the paper, but I see myself as something that we've kind of been building up to, is this idea of finite sample expressivity, right? The idea that after you define the network, and if you give it a finite number of training examples, there is some universe, some set of functions it's able to learn, right? Based on that structure and on that finite number of data points. And what they show, and they do this actually mathematically, is that as soon as the number of parameters P of the network is greater than n, so as soon as you have more parameters than data points, even relatively simple networks can represent any function of the input sample, right? And they define this in a very particular way, which is why I'm showing you this little example here. What they define the function such that the label that you get from applying the network to this input is the same label you get in the data, right? So that's why I'm giving this example with the overfitting polynomial, because the polynomial that you get is exactly touching each point exactly once. So it's giving you the exact answer for all those cases, and it's giving something completely wrong everywhere else, right? So this is kind of the same idea. And they formalize this in the theorem that you can always come up with a 2-layer rectified linear unit network with 2n plus d weights that can represent any function on a sample size of n in d dimensions. So what this means is you can always find kind of a polynomial like this one that somehow is memorizing enough of the data to give you the correct answers for the training data set, always. Even though, of course, like as we saw already, for the testing data set, it will give you nonsense answers.
Mm-hmm.
So,
and further, they suggest that there are some transformations that you can use if you want deeper networks than wider networks that will produce the equivalent network.
Yes.
So it's not just applicable for two-layer networks.
Yes, and then, so they proved that you can do this for two-layer networks, and then and then of course you can generalize to higher dimensional ones.
Right.
And deeper structures. So to summarize, deep neural networks can easily fit random noise, which is surprising. Optimization random labels actually still works, but slower. So it kind of has to figure out that you're messing with it in the beginning. Networks with more parameters than data points have enough expressive capacity to completely memorize the data to give you always the right answer for the training. Stochastic gradient descent, I didn't really talk too much about here, acts as an implicit regularizer. So it's biasing you towards having lower weights with lower norms, with smaller norms. Explicit regularization has a small effect, so it doesn't give you that big of an improvement. And yeah, like I said, stochastic gradient descent always converges to a solution with small norms, and I think that's it. So if you have any more questions, I'm more than happy to answer them. I hope I didn't go over time, but I think that's...
No, you finished right on time.
Excellent.
I've got a question, but I'll open it up before I ask mine to anyone who'd like to jump in. Anyone? So one of the questions that I had came up in some of the formalization elements of this. They talk about, in a couple of places, shattering, like something shatters something else. I can't find it anymore, but I looked it up on Wikipedia, and it's related to this prior work on Vapnik-Chervonikis theory, and has to do with set theory. Does that mean anything to you?
I know nothing about this, actually. I mean, okay. I found it on the paper, and just says that it's so the way they're saying it is, so, and this is in the related work, so, which I didn't go into too much depth. There they say Bartlett 1998 proved bounds on the fat shattering dimension of multi-layer perceptrons with sigmoid activations in terms of the L1 norm of the weights at each node.
Yeah, so they mentioned the fat shattering a couple of times, and they mentioned the, let's see if I can pull it up in the paper. They mentioned, the other, just shatter, something shatters something else a couple of times in the paper, but I couldn't quite figure out what that was referring to.
So the only, then there is one.
Okay, so here in, where is this saying?
I mean, the only time the chatter appears afterwards is in the conclusions. They say the experiments we conducted emphasize that the effective capacity of several successful network architectures is large enough to shatter the training data.
Right. Yeah. Yeah. That was the other. They talk about fat shattering twice, and then this shatter the training data once, and I wasn't quite sure what that meant.
I'm not entirely sure either, actually.
Okay. Any other questions before we finish up? All right. Well, Bruno, thank you so much. That was a great presentation. I really appreciate you taking the time and answering all the questions. Great job.
And if you guys have more questions, feel free to reach out to me. I mean, I'm easily found online. So.
Awesome.
And I'll post the PDF of the slides in the Slack group so that you guys can take a look at it more carefully.
Okay, and we'll get the video posted as well. If that, we had some problems with the video last time, but assuming everything is good with the video this time, we'll get that posted as well.
Excellent.
All right. Thanks, everyone.
Thank you.
Bye-bye, and
Thanks,
happy New Year, happy holidays, and all that
Happy
good stuff.
holidays.
And looking forward to seeing y'all next year.
Looking forward to. Bye.
Bye-bye.
Thanks, Sam.
Thanks. Happy holidays, everyone.